All right, guys, and welcome to our next chapter on advanced integration strategies. So today we're going to talk about something called integration by parts, and this is basically like a product rule that works for integrals. And this is going to kind of help us answer the question, like, how could I do some integrals that look relatively simple, but should be doable, right? How would I integrate x times sine of x? Or how do I integrate natural log of 4x? Or how do I integrate x squared times e to the x? So like these all seem like integrals that we should be able to do. And in fact, integration by parts is the strategy. So there is a formula we're going to use for integration by parts. But let me go ahead and show you where it comes from. So we're going to start with the product rule. So the product rule says if you have two functions, let's call them u and v. If you take the derivative of u times v together, and I differentiate my u's from my v's by putting a little line down on the u's. So the derivative of u times v is u times the derivative of v plus v times the derivative of u. Now, if you're feeling kind of frisky, maybe you just try and integrate this. Like for fun, we have an equation. Let's try and integrate everything. Just integrate both sides. So on the left side, the derivative and the integral cancel. So we get uv equals integral of u dv plus integral of v du. So now if we just try and solve for this integral, subtract that to the other side, we get the integral of u dv is equal to uv minus the integral of v times the derivative of u. This is our key formula for integration by parts. Put a big star by this in your notes. This is the formula we're going to kind of plug and chug in. And the way that I remember this formula is you're basically doing the ultraviolet voodoo. So the ultraviolet voodoo, it's like a special dance, and that's how you can help yourself remember this formula. Okay, this is a very powerful tool. Other than USub, this is probably the most common integration strategy that you'll use on challenging integrals. So let's go through and use some examples. So suppose we ask, let's just do the first one I did, the integral of x times the sine of x. Okay, so when you have something like this, you're thinking this is like your starting point. You're starting with the integral u dv, and like a u-sub, you're going to just try and identify which part is which, so you can go ahead and use this formula. So your first step are to pick the u and the dv from this formula. Okay, so just some choices for picking these, or some tips for picking these. So when you pick u, pick something that is going to go away when you take a derivative. So the u goes away when you take a derivative. So probably the most common thing you'll see for u, the most common thing you'll see is like a polynomial, but the first choice that you always want to use and see is a natural log of x. Natural log of x goes away beautifully when you take a derivative of it, so that's kind of your obvious choice. So natural log of x, polynomial, inverse trig functions, those are like the general strategies you'll use for u. Okay, and then when you pick your dv, what you might want to do here is pick something that is easy to integrate. So pick something that is easy to take the integral of. Usually this will be something straightforward. The most common ones you'll pick would be something in the form like an e to the u. Sometimes you'll pick like a trig function. And sometimes you might even pick like just the dx itself. And we'll look at an example of that in just a minute. So those are examples of what you pick for that. Okay, so in this case, this is the first problem. The u we're going to choose is just x because that just goes away nicely when you take a derivative of it. And then the dv, we're going to pick that to be just sine of x because, again, it's pretty easy to integrate that. And the dx is going to come there. Okay, so after you've chosen your u and dv, and we'll talk about different strategies for that today, then what we'll do in the next step is we'll integrate dv to get v, and then we'll differentiate u to get du. Okay. So if we were to take the derivative, so you notice how I kind of wrote the u up top. I'm going to write the original functions up top and the derivatives down below. So if you take the derivative of this, right, we know that du dx is just equal to 1. So my du is just equal to 1 times dx. Okay. And then for my v, if I were to integrate this, I get my v, the integral sign, we know is negative cosine of x. Okay. We're not going to put the plus c. We're going to put the plus c in at the end. So I'll put there's no plus c yet. Okay. yet. So once I've done that, once I have my v and I have my vu, then all I need to do is just plug in the formula. So all these problems are going to kind of have the same strategy now. Once we start with u and the dv. In blue, I found the v and the du. So now I'm just going to go to the formula. It's the ultraviolet minus the voodoo. Okay, so the uv, I'm going to put both of those in. So u times v, so that is negative x cosine x minus integral of v du. So minus the integral of minus cosine x times a 1 dx. Sorry about the little dot there. Okay, and you might be crying foul and say, well, Boris, there's still an integral. This is stupid. But I want to point out this is a much simpler integral, right? This just has you do negative x cosine x plus the integral of cosine x. You guys know how to integrate cosine x. So that's the point of integration by parts. You take a complicated integral and you apply this formula and you turn it into an integral that's easier to do. So this is just negative x cosine x plus integral of cosine is just sine of x plus c. And there you go. So you plug in your formula, you do the integral, and you are good to go. Okay, so that's how you approach this problem. And that, my friends, is the integral of x sine x. And if you want to take the product rule and differentiate this to check your work, you can, and you'll see it works out. Okay, so let's go ahead and let's go to the next problem here. So the next problem here, let's say just for example, you want to integrate natural log of 5x dx. Now, this one's a little trickier, but if you see an ln, always choose that to be your u. So I'm going to pick my u in this case to be just the natural log of 5x. Well, then what do we have left, right? Once we picked that to be my u, then the dv that we're going to pick, remember we're always starting with the u dv. We're starting with the left side. The dv I'm going to pick is just dx. There's nothing else that I really have left here. Okay, so now when I take the derivative of this, the derivative of ln of 5x is just 1 over 5x, and then by chain rule, multiply derivative of 5x, which is 5. So the du is just a 1 over x dx. The 5's cancel out. Okay, and then when I integrate the dv, I'm just integrating like a 1 dx, so my v is equal to just x. Okay, so again, I wasn't left with anything, so that was just what I had to pick to be my dv, and you're just it's a dx is just like a 1 times dx, so it just integrates to be x. Okay, so now that I've done this, I have my u, I have my v, let's use the formula. So my formula tells me this will be the ultraviolet voodoo. Okay, so this is going to be x times the u was ln of 5x, okay, minus integral v du. So I'll be integrating x times 1, oh my goodness, look at that, just beautiful. So this becomes x ln of 5x minus integral of just 1 dx. So again, the integral just got way easier. So this is just x ln 5x minus x plus c. Okay, now my friends, that is how we would integrate natural log of 5x or ln x or something like that. Beautiful. Okay, let's look at another example here. Let's go ahead and try integrating x squared e to the x. And you might want to go ahead, pause the video, try this problem on your own, see how far you can get. Okay, so when you see a problem like this, anytime you see an e to a power, e to the x, e to the 2x, that should be your dv. So let's pick that to just be e to the x dx. And then your u, obviously, is just the dx always is in the dv. So dx is in the dv always. It's just always going to be part of it. You're going to bring that along. Okay, and then my u is the x squared. Okay, something magical is going to happen here, by the way. So when you take the derivative of x squared is 2x dx. And then when you integrate e to the x, of course, it's the easiest integral in the world. You just have e to the x. Again, we're saving the plus c for the end. Okay, so we've done those. Let's go ahead and pull this in. So we got a uv minus integral voodoo. So uv, so that's x squared times e to the x minus integral v du. So that's 2x times e to the x dx. And at this point, you might be flummoxed. You might be frustrated. How do I do this? But, well, I'm making progress, right? Like, if this integral looks more complicated than your original integral, you screwed up. And that's an indication that you should choose a different value for u and v, or u and dv. But in this case, the integral's a little easier, right? We have an x instead of an x squared. But now, what you're going to do is you're going to do integration by parts again on this. really fun. You might get to do it twice. You might even get to do it 3 times. So the general strategy here is you're still going to have the x squared e to the x minus, and then you just need to do integration by parts again on this one, on the integral of 2x e to the x. Okay, well this is a beautiful problem. So the u is 2x, that's going to go away. The du is a 2 dx. My dv is e to the x dx, and my v is just e to the x. Okay, so that becomes uv, so 2x e to the x minus integral v du, so that's 2 times e to the x times the dx. Wow, just stunning beauty on this problem, right? This is why you took this class. So you could see awesome problems like this. Don't forget to distribute the minus, that's crucial. Where you get to do integration by parts multiple times, just fantastic. This integral, of course, is really easy. Minus minus is plus 2e to the x plus c. Fantastic. So in this point, we got to do integration by parts twice. What a sick problem. Okay, let's do one more here. What if some chump asks you to integrate inverse tangent of x? Well, gee, you might say, I remember how to take a derivative, but how do I integrate? That should be straightforward. Well, I'll show you how. You just pick u to be the inverse tangent of x. And of course, you're a good student, so you remember the derivative is 1 over 1 plus x squared. All right, and then the dv, well, there's none on the left. The dv is just a dx. So then when I go ahead and integrate that chump, I'm going to get my v as just x. Okay, so when I set up my uv, minus integral v du, so this just becomes x times inverse tangent of x minus integral v du, so minus integral of x over 1 plus x squared times dx. And then you're like, oh, geez, well, that's a totally different integral. But, oh, I could do this integral with a u sub, right? You can look at this and say, oh, I could just choose u to be 1 plus x squared, and then the derivative of that would be a 2x dx. So we get to bring in a new strategy here. So we put a 2 here, we put a 1/2 in front. So the integral just becomes 1/2 integral of 1 over u du. I know it's unfortunate you have like a u and a u sub and a u in like the parts. Sorry about that. Blame the math gods. Anyway, but that just becomes relatively easy. We know how to integrate that. That's just 1/2 times ln of absolute value u. We'll make sure we pick the u we did for the u sub. So this becomes x inverse tangent of x minus 1/2 natural log of absolute value 1 plus x squared. My friends, that is how you integrate inverse tangent. And who would have thought there'd be a natural log? That's freaking sick. Okay, so that's integration by parts. And you're going to use this strategy if you have a product. So you're going to use integration by parts if you have a product, but a u sub doesn't work. So throughout this chapter, we're going to learn a lot of strategies, and we want to think about when do we apply each one, and that's our key for integration by parts. Okay, I'll do some definite integrals in the next video. Thanks for watching, guys.